Chapter 2. What a stroke actually takes. Imagine one of the world's great orchestras in full flight, 100 musicians, each with their own instrument, their own part, their own timing, held together not by any single player, but by the constant, instantaneous exchange of acoustic and visual signals between every section simultaneously. First violins responding to cellos, woodwinds cueing brass. Percussion anchors the whole. The conductor's baton does not produce the music. It coordinates the network of relationships through which the music produces itself. Now imagine that 12 of the string players suddenly fall silent, not because they have forgotten their parts, not because their instruments are broken, because the acoustic pathway through which they heard the rest of the orchestra, the signal that told them when to enter, when to soften, when to sustain, has been severed. The musicians are still there, their instruments are intact, their training is undimmed, but they are playing in isolation, disconnected from the living web of cues that made their contribution meaningful. What you hear from the auditorium is not simply a slightly quieter orchestra. You hear something qualitatively different, an ensemble that has lost its coherence. Notes arrive slightly mistimed. Sections that previously integrated seamlessly now sound like separate entities attempting, with increasing effort and decreasing success, to approximate a whole. The experienced listener hears not just the absence of 12 musicians, but the disruption of every relationship that depended on them. This is what a stroke actually takes. The brain is not a collection of parts. For much of the 20th century, the dominant framework in clinical neurology was essentially localizationist. The brain was understood as a collection of functionally specialized regions, each responsible for a specific capacity, and brain injury was understood as the loss of whatever function resided in the damaged area. Damage to Broca's area, expressive aphasia. Damage to the primary motor cortex, contralateral motor deficit. Damage to the visual cortex, visual field loss. This framework was not wrong. It was a genuine and productive scientific advance, but it was incomplete in ways that have taken decades to fully appreciate, and that have enormous implications for how we understand and treat stroke recovery. The brain is not a collection of functionally isolated modules. It is a network, or more precisely, a network of networks. A complex, dynamic, hierarchically organized system in which virtually every cognitive and motor function depends not on any single region, but on the coordinated activity of distributed circuits whose components may be physically remote from each other, but are functionally inseparable. Vision is not in the visual cortex. Language is not in Broca's area. Movement is not in the motor strip. Each of these functions is the emergent property of a network whose nodes are distributed across multiple brain regions, whose connections traverse subcortical and white matter pathways, and whose operation depends on the precise temporal synchronization of activity across all its components simultaneously. Resting state networks. What a stroke actually takes. The brain's default architecture. One of the most important discoveries in 21st century neuroscience was the identification of resting state networks, large-scale functional circuits that remain organized and active even in the absence of any specific task. The default mode network is active during self-referential thought and internally directed cognition. The salience network monitors the environment for relevance and threat. The central executive network supports working memory and goal-directed behavior. The sensorimotor network maintains the readiness for movement. The dorsal and ventral attention networks allocate cognitive resources across the perceptual field. These networks are not metaphors. They are anatomical realities, defined by consistent patterns of correlated activity, measurable with functional MRI, electroencephalography, and magnetoencephalography. They were present before you began reading this chapter. They are operating as you read it. Their coherence, the degree to which their component regions are firing in synchrony, is one of the most reliable predictors of cognitive performance, emotional regulation, and neurological health across the lifespan. And they are precisely what stroke disrupts, not as a secondary consequence of focal tissue damage, but as a direct, immediate, and often global effect of the network architecture being fractured at one or more of its critical nodes. A stroke does not create a hole in the brain. It creates a fracture in a network. and the consequences of that fracture propagate far beyond the site of injury, through every circuit that depended on the damaged connection. Disconnection, when the pathways go silent. The concept of disconnection syndrome, neurological deficits caused not by the destruction of functional cortical tissue, but by the interruption of the white matter pathways connecting that tissue to other regions, was introduced by Norman Geschwind in a landmark series of papers published in the 1960s. Geschwind argued that many of the most puzzling clinical presentations in neurology could be explained not by focal cortical damage, but by the severing of the anatomical connections between otherwise intact cortical regions. Half a century of subsequent research has confirmed and extended this insight to a degree Geschwind could not have anticipated. Modern diffusion tensor imaging, which maps the white matter pathways of the brain with extraordinary precision, has revealed that stroke-related white matter damage is both more common and more consequential than was recognized in the era of structural MRI alone. A stroke that appears on conventional imaging as a relatively contained cortical or subcortical lesion may simultaneously interrupt dozens of long-range white matter tracts, severing the functional connections between regions that are themselves structurally intact. The scale of disconnection. The practical implications of this are profound. Consider the corticospinal tract, the primary descending motor pathway running from the motor cortex through the internal capsule to the spinal cord. A small lesion in the internal capsule, sometimes no larger than a centimeter in diameter, can disconnect the motor cortex from the entire contralateral body. The motor cortex is structurally intact, the spinal motor neurons are intact, the muscles are intact, but the pathway that connects intention, what a stroke actually takes to action, has been severed, and the functional consequence is complete or near-complete hemiplegia. Now consider what happens to the networks that depended on that intact motor cortex. The cerebellum, which receives a copy of every motor command to refine the next movement, is no longer receiving those commands. The basal ganglia, which modulate motor initiation and selection, are now operating without the cortical input they require. The supplementary motor area, which plans complex movement sequences, is planning for an execution pathway that no longer functions reliably. The disconnection does not stay local, it propagates. The emerging consensus in post-stroke neuroscience reflects this reality, that the functional consequences of stroke cannot be predicted from lesion anatomy alone, and that recovery trajectories are better understood and better targeted when network architecture is the primary unit of analysis rather than the individual lesion site. The functional consequences of stroke cannot be predicted from lesion anatomy alone. Recovery trajectories are better understood when the network, rather than the lesion, is the primary unit of analysis. Why minimal residual lesion does not mean recovered. This understanding resolves one of the most frustrating and common experiences in post-stroke clinical practice. The patient whose imaging looks remarkably good, whose acute deficits have substantially resolved, who has been discharged from formal rehabilitation, and who nonetheless continues to report profound fatigue, cognitive slowing, emotional dysregulation, and a persistent sense that something fundamental has changed. The statement, "Your scan looks fine," concerns structural integrity. It is not a statement about functional connectivity. A brain with a small, well-defined lesion and minimal visible structural damage may nonetheless have sustained extensive white matter disruption, widespread diascosis, and significant disruption to multiple resting state networks, none of which will appear on a standard clinical MRI, and all of which may produce exactly the symptom profile the survivor is reporting. The gap between what the imaging shows and what the person experiences is not an artifact of exaggeration or inadequate coping. It is a direct reflection of the difference between structural imaging and functional network integrity, a difference that the clinical system, for entirely understandable resource and infrastructure reasons, rarely has the tools or the time to bridge. Functional connectivity MRI studies of post-stroke patients have consistently demonstrated persistent disruption to large-scale resting state network organization in individuals whose structural scans appear largely normalized, often months or years after the acute event. The default mode network in particular shows reduced internal coherence and disrupted connectivity with the salience and executive networks in post-stroke populations, correlating directly with the cognitive fatigue, attentional difficulties, and processing speed reductions that survivors report, but that standard neurological examination fails to capture. Desynchronization, what a stroke actually takes. When the timing breaks down disconnection, the severing of anatomical pathways, is one dimension of what stroke takes. But there is a second, equally consequential dimension that is even less visible to standard clinical assessment: the disruption of neural synchrony. The brain does not communicate solely by location, it communicates by timing. The coordination of activity across distributed neural networks depends critically on oscillatory synchronization, the tendency of neuronal populations to fire in rhythmic, temporally coordinated patterns that enable efficient information transfer across the network. Different frequency bands carry different types of information. Delta and theta oscillations support memory consolidation and long-range communication. Alpha oscillations reflect attentional state and cortical inhibition. Beta oscillations are intimately linked to motor preparation and execution. Gamma oscillations underpin local cortical processing and perceptual binding. The oscillatory signature of stroke simultaneously disrupts these oscillatory patterns at multiple scales. At the level of the lesion site and peri-infarct zone, the loss of neuronal tissue and the metabolic disruption of surviving cells produce a characteristic slowing of cortical oscillations, a shift away from the faster alpha and beta frequencies toward the slower delta and theta ranges. This lesional slowing has been observable on EEG since the earliest applications of electroencephalography to stroke medicine, and it directly reflects the metabolic state of the injured tissue. But the oscillatory disruption does not stay local. The same network-level mechanisms that propagate structural disconnection also propagate desynchronization. When a node in a network that previously fired in synchrony with its partners is damaged or disconnected, the network's temporal coordination is disrupted. Regions that were previously entrained to each other, firing in consistent phase relationships that allowed efficient information transfer, now fire independently, or in degraded phase relationships that reduce the bandwidth of their communication. The consequence at the level of lived experience is precisely what survivors describe: a brain that feels slower, less fluent, less able to do multiple things simultaneously, more effortful in tasks that previously required no conscious attention. The subjective experience of cognitive fog, of word-finding difficulty, of the strange sensation that thinking has become laborious. These are not psychological responses to a frightening medical event. They are the direct perceptual correlates of a desynchronized network attempting to perform functions that depend on the precise temporal coordination it has lost. Interhemispheric desynchronization and motor recovery. Nowhere is the clinical importance of synchrony more evident than in motor recovery. The coordinated execution of voluntary movement depends on an extraordinarily precise temporal dialogue between multiple brain regions: the supplementary motor area planning the sequence, the primary motor cortex issuing the command, the cerebellum monitoring the execution and predicting the sensory consequence, the basal ganglia selecting the appropriate motor program and suppressing competing ones, the parietal cortex integrating the sensory feedback that confirms the movement has occurred as intended. This dialogue unfolds over timescales of tens to hundreds of milliseconds. Small disruptions in the temporal synchrony of these networks, disruptions far below the threshold of detection by standard clinical examination, produce measurable and clinically significant impairments in movement quality, movement speed, and the ability to perform complex or dual-task motor activities. A survivor who can walk the length of a corridor in a clinical assessment, who scores adequately on a motor function scale, may nonetheless be performing that movement with profoundly disrupted oscillatory coordination between motor, cerebellar, and sensory networks, a disruption that becomes apparent only when the task becomes more complex, the environment less predictable, or the cognitive load increases. The principle this reflects, that synchrony, not just structure, determines functional outcome, has direct implications for how recovery should be assessed, monitored, and targeted. Interhemispheric coherence in the beta frequency band has been shown to be a significantly stronger predictor of upper limb function at 6 months post-stroke than lesion volume or anatomical location alone. The orchestra revisited. What network disruption looks like from the inside. Return for a moment to the orchestra. The 12-string players who fell silent did not simply subtract their contribution from the ensemble. Their silence changed the acoustic environment for every other musician. The brass section, accustomed to cueing off the string texture beneath them, now enters slightly out of sync. The woodwinds, whose phrasing was shaped partly by the responsiveness of the strings, sound more effortful, less supple. The conductor, reading an ensemble that is no longer responding to the baton as it used to, begins compensating, making larger gestures, increasing the explicitness of cues that previously did not need to be stated. The audience hears this as degraded music. But from the musician's perspective, something equally important is happening. They are working harder. The effort required to produce a performance that is only marginally recognizable as the one they trained for is substantially greater than the effort that produced the original. The ensemble's efficiency has collapsed, even as individual players remain technically capable. This is the subjective phenomenology of post-stroke network disruption. The brain's remaining intact regions are not simply doing less, they are working significantly harder to produce outcomes that are often indistinguishable to an external observer from normal function. The survivor who presents as doing well in a clinical assessment may be doing well at the cost of a neurological effort that is consuming enormous metabolic resources, suppressing the plasticity needed for genuine recovery, and creating a pattern of compensatory activation that, if left unaddressed, becomes the default architecture of their nervous system. The dynamic reconfiguration problem. A healthy brain does not operate in a single network configuration. One of the most important insights from contemporary network neuroscience is that the brain is a dynamic system, constantly reconfiguring its network architecture in response to task demands, environmental context, and internal state. What neuroscientists call network flexibility, the capacity of the brain to rapidly and efficiently shift between different functional configurations, is closely associated with cognitive performance, adaptive behavior, and resilience under load. After a stroke, this flexibility is typically reduced. The damaged network is less able to dynamically reconfigure in response to changing demands. Configurations that were previously transient, patterns of connectivity appropriate for a specific task but not for general background function, tend to become fixed as the brain defaults to whatever compensatory architecture it has established in the acute and subacute phases of recovery. The survivor is not just dealing with a network that has been damaged. They are dealing with a network that has lost a significant degree of its adaptability. This has direct implications for the experience of recovery. The person who functions reasonably well in a predictable, low-demand environment but deteriorates sharply when the environment becomes more complex, more unpredictable, or more socially demanding is not simply having a bad day or pushing themselves too hard. They are encountering the limits of a network whose dynamic range has been narrowed by the loss of flexibility and whose compensatory configuration, optimized for survival in a simplified environment, is not equipped for the full complexity of the life they are trying to return to. The survivor who functions reasonably well in quiet environments but deteriorates in complexity is not having a bad day. They are encountering the narrowed dynamic range of a brain that has lost its capacity to flexibly reconfigure. What this means for recovery. If the problem is a network issue, disconnection, desynchronization, loss of flexibility, propagated disruption, then the solution must be a network solution. This is the fundamental insight that motivates the three-layer framework described in the second half of this book, and it is worth stating its implications directly before we explore the science that supports it. Standard rehabilitation, as currently delivered, addresses the functional consequences of network disruption. It works to restore the behaviors, walking, reaching, speaking, that have been impaired by the disruption. This is valuable and necessary work, but it does not directly address the network disruption itself. The disconnection, the desynchronization, the lost flexibility, the interhemispheric imbalance. It operates on the network's outputs without systematically addressing the architecture that produces them. This is not a criticism of individual practitioners who work with exceptional skill within the constraints of what the system provides. It is a structural observation about the level at which the current rehabilitation framework intervenes, and about the level at which a genuinely complete recovery program must also intervene. Targeting network recovery requires, first, an understanding of the network architecture that stroke has disrupted and the hierarchical sequence in which that architecture was originally built. Not as a treatment ladder, but as a map of interdependencies. That architecture is the subject of the next chapter. It also requires something that current rehabilitation systems rarely provide, a framework that engages all levels of that hierarchy in parallel, including the brainstem, the vestibular system, spinal reflexes, and autonomic regulation, which constitute the substrate on which all higher network function depends. Because the natural neuromotor hierarchy builds from the bottom up, and because these foundational structures are frequently intact but underactivated following stroke, initial clinical emphasis naturally falls on layer 1, not as a precondition that must be completed before addressing higher function, but as the level where the investment is proportionally greatest at the outset, shifting upward as the network reorganizes. You cannot resynchronize an orchestra by giving each musician better headphones. You need to restore the acoustic environment, the shared medium that enables coordination. In the nervous system, that acoustic environment is the integrated activity of lower-level networks that provide the substrate for higher-level synchrony to be rebuilt. The following chapter maps that architecture, the evolutionary and developmental sequence through which the human nervous system built its network hierarchy from the brainstem upward. Understanding that sequence is not a prescription for treating one layer at a time. It is a map of how all 3 layers must be engaged together, each restoring what the others depend upon, with the natural emphasis of the clinical work initially weighted toward the foundational level from which the hierarchy ascends. To attempt recovery from the cortex downward is to ignore the direction in which the system was built, and to accept, by default, a program of compensation rather than directed neuroplasticity.